डियर स्टूडेंट्स, वेलकम टू PHY367। आज हम देखेंगे रैंडम वॉक और बाइनॉमियल डिस्ट्रीब्यूशन। रैंडम वॉक और बाइनॉमियल डिस्ट्रीब्यूशन दे बोथ आर कनेक्टेड और इनको जानना हमारे लिए बहुत ज़रूरी है। रैंडम वॉक की एक स्टैंडर्ड डेफिनेशन है, वो जैसे कि इसके नाम से ज़ाहिर है कि रैंडम वॉक एक प्रोसेस का नाम है। मैथमेटिक्स में इसकी और तरह की डेफिनेशन है, हम मैथमेटिक्स बाद में करेंगे। वक्ती तौर पे हम फिज़िक्स इसकी जानने के लिए कोशिश करते हैं, थोड़ा सा इसको समझने की। So a random walk is the process by which randomly moving objects wander away from where they started. So that's their standard definition. अब ये डेफिनेशन हमारे लिए क्यों हेल्पफुल है? हम फिज़िक्स में पढ़ते हैं गैसेस की में पार्टिकल्स, फ्री आइडियल गैस, फ्री पार्टिकल्स, इस तरह की चीज़ें, और हमें वास्ता पड़ता है मॉलिक्यूल्स का, एटम्स का, आयंस का, आपस में मूव कर रहे होते हैं, आपस में कोलाइड करते हैं, और दे आल्सो कोलाइड विद द वॉल्स ऑफ द कंटेनर, एंड एवरी molecule, if it starts from here, it goes through a number of collisions with other molecules, and with, if there is a container, with the walls of the container, and we have to predict its final position somehow. So we should have some knowledge of probability theory to predict that. Okay, this is the one reason. There are certain other reasons that we will discuss later, but okay, so for the start, you can keep in mind that this is the scenario where we wanna start. So for random walk, इसके लिए कुछ सपोजिशंस हैं जो हम करेंगे पहले इसकी मैथमेटिक्स को समझने के लिए, और फिर एक छोटी सी एनिमेशन देखेंगे हमारा जो मैथमेटिक्स है उसको स्टार्ट करने के लिए। तो सपोजिशंस क्या हैं कि एक ऐसा एक्सपेरिमेंट जिसके जस्ट दो ही आउटकम्स हों, एक ऐसा एक्सपेरिमेंट जिसके दो ही आउटकम्स हों, तो उसको हम कहते हैं बर्नौलीज़ ट्रायल। तो मैं लिखता हूँ Bernoulli's trial, which has only two outcomes. Example of this is we have this coin toss, so we can get either heads or tails. और जब हम रैंडम वॉक को डिस्कस करना चाहेंगे, इसको हम बाइनोमियल एक्सपेरिमेंट भी कह सकते हैं, तो इसमें ये होगा, मैं लिखता हूँ ये, इन चीज़ों की एग्जैक्ट मीनिंग आपको बाद में समझ आएगी, वक्ती तौर पे आप इनको जस्ट ध्यान में रखेंगे इसका क्या हो रहा है। अब बाइनोमियल एक्सपेरिमेंट में इसकी डेफिनेशन लिखने लगा हूँ और इसके साथ जुड़ी हुई सपोजिशंस में लिखूँगा। सो बाइनोमियल एक्सपेरिमेंट में पहली सपोजिशन ये है कि इसमें हमारे पास नंबर ऑफ बाइनोमियल ट्रायल्स होते हैं। एक बाइनोमियल ट्रायल नहीं बल्कि एक से ज़्यादा बाइनोमियल ट्रायल्स होते हैं, लेकिन एक फिक्स नंबर लेते हैं। सो अ फिक्स्ड नंबर ऑफ Bernoulli trials Number 2 is each trial is independent from any other trial. I mean, एक की प्रोबेबिलिटी का दूसरे की प्रोबेबिलिटी पे कोई फ़र्क नहीं पड़ता, दे आर इंडिपेंडेंट। सो हम एक कॉइन को 10 दफ़ा टॉस करें या हम 10 कॉइन्स को बैक वक्त टॉस करें, तो उनके आउटपुट्स का या आउटकम्स का एक दूसरे से कोई ताल्लुक नहीं होता, दे आर ऑलवेज इंडिपेंडेंट। और हर ट्रायल के, मतलब सब बर्नौली ट्रायल, सो देर आर ओनली टू आउटकम्स ऑफ सिंगल ट्रायल। और So what we do, the property of each the other property of this is the probability of each trial remains constant. From trial to trial. That means if we have, for example, in case of a coin toss, we have 1 by 2 probability of getting a heads or a tails. When we do a lot of trials, the probability of each trial remains the same. Okay, so for first trial we had the probability 1/2, and even for the 10th or 20th or 50th trial, the probability should remain 1/2 for each outcome. So that's the scenario for this kind of experiment. So these are the supposition that we will take with us, and now I show you a simple animation to understand binomial distribution in one dimension. So you should call it a random walk in one dimension, because at the end of the day we will get somehow something relevant to binomial distribution. So for the time being we say, okay, this is the example for random walk in one dimension. So I show you a simple animation. So we have a scenario that I made like a small animation for this. So we have a scenario in which we have a hungry cat. You see here, she looks very fierce, and she's hungry and she wants to eat something, and she has some experience of eating birds. And where are those birds? So we have one dimensional case. So we have two apple trees on two sides of the cat. So cat stands in somehow in the middle of the two trees, and those two trees are located somehow at equal distances, and there are two birds like this. They are somehow hovering over the trees, and our cat has her eyes on those birds, so she wants to eat both of them, or whichever she can catch first. And they are normally above the trees. If you can see, they are above the trees, but they have a habit that they come down somehow after some time, randomly. So it's totally random when they will come down, and the cat can see them, and whenever one of them comes down, it may walk toward them. So for example, it sees this bird coming down, it will walk toward this, and if whenever it sees it's going back up there, it somehow moves, the cat moves back. So suppose the bird on the cat's right hand side is down somehow, and our cat can catch it, and it somehow starts to move in this direction, and it takes one or two steps, and the bird can also somehow observe cat coming, and it goes back up again, and the cat has no choice but to go back somehow after looking at it. So it is somehow disappointed, and it goes back, and now it sees somehow the other tree, and it somehow it can judge that the other bird is somehow in its reach. So it starts to move into the other direction. It takes a couple of steps, and the bird is again clever, and it goes up when the cat comes near, and the cat is disappointed again. I can show you the disappointment on the cat's face. Oh, she's angry, and now she decides to go back to her initial position. Somehow it takes a couple of steps back, and it reaches the middle point again, and stays there, and waits when some other bird from either side comes down. So the point here is that the motion of cat is very random, and it can go in either direction from the middle point. And after like sufficient time has passed, for example half an hour, 1 hour, so it has taken so it can move either in one direction, either to its right or to its left. So it has no other option to go forward or backward. So that's the ideal situation that we have created. And the point is, after some time, the we should be able to predict the position without actually observing the cat. So somebody tells us, okay, it has taken 50 steps overall, and it has taken some steps to the right, and it has taken some steps to the left, but we have to predict where the cat is after some time, after 50 steps or after 100 steps. So to predict that thing, we have to use our random walk model. It's a mathematical model, and it will help us predict the motion of the cat after 50 steps or after 100 steps or after 200 steps. And this will be done mathematically, and you should be able to keep this picture in your mind, which I have given you. The central position, something to move toward right, something to move toward left, and there from we will start our mathematical journey. So for random walk in one dimension, I have to draw the same situation that I showed you in any animation, in the form of a one-dimensional curve. So here is the central position of the cat. The x is equal to 0 position signifies the cat where it was at the beginning, and now we impose somehow another restriction that the cat can move in discrete steps. So it can move from 0 to the right or to the left in discrete steps. And each step has some specific length, the same length, L. Each step has specific length L, and it can take steps towards right or towards the left. So if we call this steps toward right as n1, so here in this direction it can take whatever steps, we call the number of steps n1, and in this direction we call this number of steps as n2 number of steps. And after some time, the total number of steps, so we can write, okay, total number of steps, mathematics, we have to do small mathematics. So total number of steps is n, and this is actually equal to n1 plus n2. So it has taken n1 steps towards right and n2 steps toward left. So we call this equation 1. And the displacement after n steps is given by x, which is equal to ml. L, you know, L is the distance of one step, and okay, we call this equation 2, and m is an integer which has a value between minus n less than equal to minus n2 less than equal to plus n. So m can have a value between these two numbers, and we need to find, our problem is we need to find, okay, so we can define em like this, m equals n1 minus n2. So that we do before defining anything else, and before our problem statement. So our problem statement is we need to find the probability of finding the cat after it has taken n1 steps. So we call this probability as P. Total number of steps are n, and if it has taken n1 steps to our right or toward cat's left. So cat is moving left, and this is our, if we are looking at it, this is the our right direction. So we need to find the probability where the cat would be after taking n1 steps, where we have total steps equal to capital N. So this is the problem statement. And what else we know from equation 3, if you can see, our m is n1 minus n2, and if we put the value from equation 1, if we use equation 1, so we'll get n1 minus n1, that is 2n1 minus n. This is again another definition of our this integer that we will use to calculate the position x. So okay, we can call this equation or equation 4. Another thing that you need to keep in mind that, okay, so we have steps of equal length on each side, and we have equal probability of either moving to the right or moving to the left. So how we write this mathematically? So probability of one step or each step to our right is, we call this probability P, and probability of each step to our left, we call this probability Q. And I write this, okay, on the graph so that you should remember. So for this we have a probability P, and for this we have a probability Q. Okay, I go back, and we can write Q also as total minus the probability towards right. So at the end of the day we should know that total probability P plus Q is 1, or P plus Q, if there are n steps, it is still 1. That we should always remember. Okay, so let's suppose we pick a sequence. Let's take one of the special sequence of steps. I mean, you see that a cat goes 4 steps to the right and 3 steps to the left, for example. So it goes one step right, second step right, third step right. Okay, but it has no particular sequence, so it goes two steps to the right, then one step to the left, then again step to the right, again to the left, and again to the left. So I show them with arrows, and I mark the steps to the right with red and to the left with blue. So how much is the total probability in this case? So we have to multiply the probabilities. So P for this step, P for this step, and P for the third step, and we have Q for the blue step, Q for the blue step, and Q for the blue step. So for the sequence of steps in which we had 3 steps to the right and 3 steps to the left, so we have to get the total probability for this special set. I write it. Okay, so probability for the sequence, or not sequence, but okay, for the combination when a cat, I should write the cat, takes 3 steps to right and 3 to left, that would be given by the multiplication of these probabilities, 3 to the right and 3 to the left. And if it has, now we generalize this, if it takes and 1 steps to the right and 2 steps to the left for any combination. So it can be any combination in which it takes and 1 steps to the right and 2 steps to the left. So probability will be equal to what? P to the power n1 times Q to the power n2. ये बात आपने पढ़ रखी है प्रोबेबिलिटी में. इस केस में हम प्रोबेबिलिटीज़ को मल्टीप्लाई करेंगे और कितने फैक्टर प्रोबेबिलिटी मल्टीप्लाई होगी, जितने वो स्टेप्स ले चुकी होगी, रेज टू द पावर दैट नंबर ऑफ स्टेप्स. ठीक, अब ये क्या है, इसको मैं लिख देता हूँ एक और दफ़ा. ये जो चीज़ मैंने लिखी है, इसी चीज़ को मैं शॉर्ट फॉर्म में लिख देता हूँ रेड फॉन्ट में कि दिस इज द probability of any random combination. हमें नहीं पता कौन सा कम्बिनेशन है, हमें नहीं पता n1 कितना है, हमें नहीं पता n2 कितना है. तो कैट जो है वो इस तरह के कई कम्बिनेशन बना सकती है. यू शुड रिमेंबर कैट इज एबल to make as many number of combinations. It can take 2 steps to right, 4 steps to left, or it can take 3 steps to right, 10 steps to left, depending upon how many total number of steps we have. So हमें नहीं पता कि ये कौन सा कम्बिनेशन है, लेकिन जो भी कम्बिनेशन आएगा उसके लिए प्रोबेबिलिटी किसी भी एक रैंडम कॉम्बिनेशन के लिए प्रोबेबिलिटी जो है वो है p टू द पावर n1 टाइम्स n टू द पावर q टू द पावर n2। ये आपने याद रखना है। और अब हमने ये देखना है, हमारे प्रोबेबिलिटी का नॉलेज यहाँ पे टेस्ट होगा कि हाउ मैनी कॉम्बिनेशंस द कैट कैन मेक। तो किसी एक कॉम्बिनेशन की प्रोबेबिलिटी है ना जो हमने ऊपर लिखी, तो कितने कॉम्बिनेशंस कैट बना सकती है। कैन मेक if it has to cover n total steps। n भी हमें नहीं मालूम, n भी 10 से लेके 5 से लेके 10 और 10 से लेके 100 तक हो सकता है। तो हमने ये जानना है कि इतने स्टेप्स अवेलेबल हों तो इस तरह के कितने कॉम्बिनेशंस वो बना सकती है कैट, कितने स्टेप्स टू द लेफ्ट और कितने टू द राइट। ये हमने गैस करना है अपने प्रोबेबिलिटी के नॉलेज से, जो हम पहले कॉम्बिनेटोरिक्स में सीखा था हमने। तो इसके लिए आपको ये जानना ज़रूरी है कि अगर कैट रैंडमली मूव कर रही है, फर्ज करें टोटल नंबर ऑफ स्टेप्स 10 है, 10 तो बहुत ज़्यादा हो जाएगा, तो चलें हम इसको कंसिडर करते हैं टोटल नंबर ऑफ स्टेप्स हैं इसके पास 3। तो 3 स्टेप्स में ये तीनों स्टेप्स इस तरफ भी ले सकती है, 2 स्टेप्स इधर और 1 स्टेप इधर, इस तरह ये कॉम्बिनेशन भी बन सकता है। इस तरह ये कॉम्बिनेशन भी बन सकता है, इस तरह और कौन सा कॉम्बिनेशन बन सकता है, ये सिचुएशन भी हो सकती है। मैं तमाम पॉसिबल कॉन्फ़िगरेशंस बना रहा हूँ जो कि पॉसिबल हैं 3 स्टेप्स अगर हों। हाउ मच n इक्वल 3 हो तो आपको ये तो पता है कि कितने टोटल अरेंजमेंट्स बनेगी इस केस में। आपका नॉलेज आपको बता सकता है इस बारे में बड़ा क्लियरली। और यार इसके तीनों स्टेप्स टूवर्ड्स स्टेप 2। तो ये तो वो हैं जब इसने एक स्टेप आगे लेना है और एक स्टेप पीछे लेना है और टोटल 3 स्टेप्स ले सकती है कैट। तो ये टोटल पॉसिबल अरेंजमेंट्स हैं। अब हमें ये पता होना चाहिए कि जब हम प्रोबेबिलिटी कैलकुलेट करेंगे किसी एक स्टेप की, जब हम प्रोबेबिलिटी कैलकुलेट करेंगे किसी भी एक स्टेप की, तो अब आपको ये पता होना चाहिए कि ये 3 स्टेप्स और ये 3 स्टेप्स हमने चूँकि मल्टीप्लाई करना है ना सिर्फ, इन तीनों केसेस में जो प्रोबेबिलिटी आएगी वो कैसे होगी, इन तीन में आएगी पी स्क्वायर क्यू, मतलब 2 स्टेप्स टू राइट 1 टू द लेफ्ट, और इन 3 में आएगी पी क्यू स्क्वायर, और टॉप वाले में आएगी पी टू द पावर 3 और डाउन वाले में आएगी क्यू टू द पावर 3। ओके, सो ठीक। सो इस केस में आप ये देख रहे हैं कि ऑर्डर मैटर नहीं कर रहा। यहाँ पे 3 स्टेप्स में से जो भी ऑर्डर हम मर्जी रखें, मतलब एक स्टेप लेफ़्ट का है और 2 राइट के हैं, ऑर्डर जो भी है, इन तीनों की प्रोबेबिलिटी का एक ही मल्टीप्लिकेशन फैक्टर आएगा। इस तरह ये जो 3 स्टेप्स हैं इनका भी प्रोबेबिलिटी का फैक्टर वही आएगा। तो इसका मतलब ये है कि हमें कॉम्बिनेशन वाला फार्मूला यूज़ करना पड़ेगा इस केस में, नंबर ऑफ स्टेप्स के केस में। सो वी विल यूज़ combinations formula to get how many combinations cat can make the cat can make out of n steps, out of n total steps। यहाँ पे आप फोकस रहें कि यहाँ पे क्या हो रहा है। और साथ ही भी पता होना चाहिए कि n1 steps to right and 2 steps to left। तो कॉम्बिनेशंस का क्या फार्मूला था? वी हैड द फार्मूला, लिखेंगे हम नंबर ऑफ पॉसिबल कॉम्बिनेशंस that is equal to n factorial divided by n1 factorial n2 factorial। सो ये फार्मूला हम यूज़ करेंगे कॉम्बिनेशंस का कि कितने कितने वो बनाएगी कॉम्बिनेशंस, और हमें ये पता है कि किसी भी एक कॉम्बिनेशन की प्रोबेबिलिटी जो है वो है p टू द पावर n1 और q टू द पावर n2। तो अब हमें ये आसान हो गया कि हम ये बता सकें कि प्रोबेबिलिटी ऑफ टेकिंग n1 steps टू द राइट, जिसको हमने n1 कहा था, वो किसके इक्वल होगी? टोटल नंबर ऑफ पॉसिबल कॉम्बिनेशंस multiplied with probability of one combination। सो हमारे पास दोनों मौजूद हैं, तो हम जस्ट उनकी वैल्यूज़ यहाँ पे इसमें पुट कर देंगे। तो टोटल नंबर ऑफ कॉम्बिनेशंस हैं n फैक्टोरियल डिवाइडेड बाय n1 फैक्टोरियल n2 फैक्टोरियल मल्टीप्लाइड विथ p टू द पावर n1 q टू द पावर n2। दिस इज आवर रैंडम वॉक प्रोबेबिलिटी ऑफ n1 स्टेप्स टू द राइट। इसी तरह का फार्मूला, बिल्कुल सेम फार्मूला यूज़ होगा n2 स्टेप्स टू द लेफ़्ट के लिए भी, लेकिन हम किसी एक फार्मूले पर फोकस करते हैं। हम जब हमसे पूछा जाएगा कि हमने राइट की तरफ कितने स्टेप्स लेने हैं, तो हम ये फार्मूला यूज़ कर लेंगे। अगर पूछा जाएगा कि लेफ़्ट की तरफ, तो स्टिल हम यही फार्मूला यूज़ करेंगे, ठीक है। लेकिन हम चूँकि किसी एक वक्त के तौर पे किसी एक एस्पेक्ट को स्टडी कर रहे हैं, तो जस्ट इस फार्मूले को आप यहाँ रखें। इसको आप इक्वेशन नंबर देते हैं। नेक्स्ट इक्वेशन है हमारे पास, अगर हमने केयरफुली इक्वेशंस को की नंबरिंग की है तो इसको हम पॉसिबल कॉम्बिनेशंस को अगर हम कहें इक्वेशन टोटल प्रोबेबिलिटी ऑफ वन स्टेप को हम कह देते हैं, हमारा इसको इक्वेशन 5 कह देते हैं। और टोटल नंबर ऑफ कॉम्बिनेशंस को हम 6 बोल देते हैं। हमारी इक्वेशन 6 ये हो गई। और जो हमारे पास रैंडम वॉक डिस्ट्रीब्यूशन है, दिस इज़ आवर इक्वेशन 7। ओके, सो ये जो रैंडम वॉक डिस्ट्रीब्यूशन है हमारी, इसी को हम बायनॉमियल डिस्ट्रीब्यूशन कहते हैं। The random walk probability distribution is called binomial distribution। It is called binomial distribution, but it is not exactly binomial distribution, because binomial distribution is a bit different. How different? So original binomial distribution is, if we write in terms of the probabilities to the right and to the left, if we have n1 steps, n steps in any direction, if we want to write p plus q to the power n, this is binomial distribution. It has nothing to do with random walk, so it should be written as n0 from 0 to n factorial n factorial n minus n factorial p to the power n q to the power n minus n. This is equation 8 is original binomial distribution. आपने मैथमेटिक्स में ये स्टडी की होगी कि कोई से दो आउटकम्स के लिए या दो वेरिएबल्स p प्लस क्यू टू द पावर n हो तो उसको हम समेशन की फॉर्म में ये लिख सकते हैं, लेकिन जो हमने रैंडम वॉक से निकाली है उसमें समेशन मौजूद नहीं है, ठीक है. देयर इज़ अ डिफरेंस, लेकिन टर्म सिमिलर है, तो हम रैंडम वॉक के प्रॉब्लम को इस तरह से कह सकते हैं कि दिस इज का काइंड ऑफ बाइनोमियल डिस्ट्रीब्यूशन, नॉट एग्जैक्टली द बाइनोमियल डिस्ट्रीब्यूशन. हाउएवर वी विल यूज दिस समेशन एंड हम देखेंगे कि ये समेशन जब हम यूज़ करेंगे तो हमें फिर ये टर्म भी हम इसको यूज़ कर सकते हैं बड़ा इजीली, और इसका फ़ायदा हमें मैथमेटिकल कैलकुलेशंस में होगा, तो हम मैथमेटिकल कैलकुलेशंस करने लगे हैं अभी. अब हम अगर लिखना चाहें, इफ़ वी वांट टू राइट, थोड़ा सा आगे बियॉन्ड जाते हैं. इफ़ वी वांट टू राइट equation 7 in terms of कैपिटल N and M, हमने ये डिफाइन किए हैं स्टार्ट में कैपिटल N और M. तो उस शेप में अगर हम इसको लिखना चाहें तो क्या करें, उसमें लिखने का फ़ायदा क्या होगा वो मैं आपको बताता हूँ, लेकिन वक्ती तौर पे हम क्या ट्रांसफॉर्मेशन करने लगे हैं, W N1 से हम इसको लेके जा रहे हैं दूसरी शेप में, और उस सम डिस्ट्रीब्यूशन को हम कहेंगे, जब हम उसको N और M की शेप में लिखेंगे तो उसको हम ऐसे लिखेंगे P की शेप में. इधर हमने W लिखा था, जस्ट नोटेशन का चेंज है, और अंदर जो वेरिएबल्स हैं वो N1 और N2 नहीं होंगे, बल्कि क्या होंगे, कैपिटल N और M. तो अब हमें पता है, हमारे पास इक्वेशन थी 1 और 2, वो कुछ इस तरह थी कि हमने लिखा था n इक्वल्स n1 प्लस n2, और m की डेफिनेशन हमने लिखी थी n1 माइनस n2. ये थे टोटल नंबर ऑफ स्टेप्स. n जो था वो टोटल नंबर ऑफ स्टेप्स थे, और m जो था वो डिस्प्लेसमेंट थी एट एनी टाइम, ठीक है. तो अगर हम इनको यूज़ करें तो लेट अस ऐड दीज टू इक्वेशंस. अगर हम इन दोनों को ऐड करें तो हमारे पास आ जाएगा n प्लस m इक्वल्स टू n1. तो यहाँ से हमारे पास n1 इक्वल आएगा n प्लस m बाई 2. और इसी तरह अगर हम इनको सब्ट्रैक्ट करें ऊपर वाली इक्वेशंस को, so we will get n minus m equals 2n2, which implies that n2 equals n minus m by 2. so change of variables यहाँ से हम कर सकते हैं बड़ा इजीली. तो अब हम w की बजाय क्या लिखेंगे, p of n. this is again the same distribution, random walk distribution in one dimension, so that is n factorial divided by n plus m by 2 factorial and n minus m by 2 factorial. Okay, here, और times p to the power n plus m by 2 q to the power n minus m by 2. इसको हम हमारा नेक्स्ट इक्वेशन नंबर दे देते हैं, इक्वेशन 9. This is again the same distribution, but now we have changed variables. For W we had variables n1 and 2, and for P we have variables n and m, so it will have some advantage later on. अब हम देखते हैं कि प्रैक्टिकली इसका मतलब क्या है, इन डिस्ट्रीब्यूशंस का क्या मतलब है. एग्जांपल है कि हम लेते हैं टोटल स्टेप्स 3 और हमसे कहा जाता है कि फाइंड द प्रोबेबिलिटी ऑफ n1 steps to the right. तो सबसे पहले हमने n1 डिफाइन करना है. So n1 is, there are total 3 steps, so n1 can take any of those values. It can have 0 or 1 or 2 or 3, and if n1 is like that, n2 would be how much? If it takes 0 steps to the right, how many steps it will take to the left? 3. If it takes 1 step to the right, you have to keep in mind that n should satisfy this equation. So you will always calculate n1 and n2 based on this. So n1 is, if n1 is given, so n2 you will calculate from this formula. So this will be 3 steps, and if it takes 1 step to the right, then it has 2 steps in this direction and 1 step and 0 here. And we can also figure out the value of m from this. So m is basically n1 minus n2. So you should remember this correspondence between these 2 steps. So you write for this sequence, m will be equal to, I write m here for your convenience. M here is minus 3 minus 1 1 and 3 again plus 3, and here I should put a mod where I wrote n values of n2. Okay, so fine, this is the values that we will use. Okay, now we use the binomial distribution to calculate probability. So W3n1, so now we are calculating when total number of steps were 3 and the probability of taking n1 steps. So for n1 0, it will have n1, I should put here n1 equals 0. It would be how much it should be? 1 over 8 W3 for 3 steps, sorry, 1 step to the right and 2 to the left, it would be 3 over 8 W3. 2 will be again 3 over 8 and W3 3 will be equal to 1 over 8. So this is, you can put the values inside this formula of W and you will get these probabilities. I have written them directly, and this is for 3 steps only, so you will get 4 different probabilities. This is the probability distribution. If you want to plot this on a probability curve, here you write n1 and here you write W3 n1. So you will get somehow, here you have 1 over 8 3 over 8 here, 3 over 8 and 1 over 8. So n1 is moving in this direction, 0, 1, 2, 3. So this is a probability distribution. So for 3 steps we have this kind of probability distribution. Okay, so if you plot it in the form of line graph, so it will look like this. And now if you increase the number of steps, say you have how many steps? 20 steps. So your probability will look like this. I have taken this graph from book. If you see the probability distribution calculated from either WN1 or PNM, so it will look like this. And what this probability shows us, if you look this graph carefully, I enlarge it for you. So what this probability shows, so this panel above 0, 1, 2, 3, these are the number of steps n1, and this is the probability in this direction. So you see that after 10 steps, you can see here 10 steps, the probability is maximum. But what that where is the cat at that time? If it takes 20 total steps, and after 10 steps, if we know that it has taken 10 steps to the right direction, where the cat should be found. So it says, if you see the displacement panel down here, it says that the cat should be now at the mean position where it started from. So if it has taken 10 steps to the right, definitely the remaining 10 steps out of 20 total steps would be to the left. So 10 minus 10, 0. So after 20 total steps, and if it has taken 10 steps to the left, definitely the other 10 steps would be to the left, and the net displacement of the cat would be 0. So the probability of finding the cat is at the starting position, and away from starting position the probability decreases. So for example, if it has taken 8 steps to the left, then it would have definitely taken the other steps to the left. So net displacement would be minus 4, 4 steps to the left. And you can judge for yourself what this implies if it has taken more number of steps. So if you take for example, it has taken 14 steps to the left, to the right, then remaining 6 steps it has taken to the left direction, and net displacement would be 8. Net displacement would be 8, but in which direction? To the right. So you can study for each step what that probability distribution implies, but that's how it looks like. And now we will calculate various values for this probability distribution, what they imply. So we will calculate average value of n1, and we will calculate the width of this probability distribution using some formulas, so we can continue with that. So मीन वैल्यूज़, डिफरेंट किस्म की मीन वैल्यूज़ कैलकुलेट करने के लिए सबसे पहले तो हमें ये पता होना चाहिए, जैसे कि तमाम प्रोबेबिलिटीज़ में होता है, कि सम ऑफ द प्रोबेबिलिटीज़ in case of binomial probability distribution is always 1. And we also know that Wn1 हमने अभी कैलकुलेट की थी, हमारी इक्वेशन 7 थी वहाँ पे, तो वो थी n factorial n1 factorial multiplied by n minus n1 factorial p to the power n1 q to the power n minus n1. सिंपली हमने हर चीज़ को n1 की शेप में लिख दिया है, और हम इसके अंदर इसको पुट करेंगे तो हमें पता चलेगा कि if sum of probabilities is 1, so then the sum of this probability should also be equal to 1. P to the power n1 q to the power n minus n1, this should also be equal to 1. And we know that if this is equal to 1, then this implies this left hand side is actually p plus q to the power n, and right hand side will be also 1. So it is self consistent. You see, 1 to the power n is 1, so everything is self consistency इसे कहते हैं, self consistency check. checked. Okay, so अब हम कैलकुलेट करना चाह रहे हैं एवरेज नंबर ऑफ स्टेप्स to the right, n1 average we wanna find out. So average लेने का तरीका हमें आता है पहले से ही, हम ये करते होते हैं कि n1 average is equal to sum over all combinations multiplied with probability and multiplied with that quantity where we of which we want to take the average. So here's average is n1, so we will multiply. This is the standard formula that we use to calculate average values. We used it actually previously a couple of times. So now we put the values. So this is n equals 0 to n factorial divided by n1 factorial n minus n1 factorial p to the power n1 q to the power n minus n1 times n1. So here we have some extra factor n1 lying here, so we need to know which factor is that. So we call this equation A, and we want to solve this. So this thing is a sum before n1, but we cannot sum it if n1 is present here, so we cannot directly sum it. We have to get rid of this n1 to do the sum again. This sum is equal to p plus q to the power n, but this n1 spoils it somehow, so we need to get rid of it. How we do that? So we do some trick. So you see here we have n1 and p to the power n1. So we write this, okay, we do some manipulations to this thing. So we have n1 times p to the power n1. What we can do here, we can write this as p times partial over partial p, again p to the power n1. So these two things are exactly similar. You can evaluate this differential here, and you will get back this value. So now what we do, we just replace this quantity with this one in equation A here. So let's do it. So we get n1 average equals n0 to n factorial. I write everything as it is. So instead of writing p n1, I write p partial over partial p to the power n1, and we write q as it is, that was already written. We don't change anything in the term of q, in terms of q. So you see this differential here, it has nothing to do with q. So we can take this whole thing all the way back here before the summation. So what we write? So we write p partial over partial p summation n factorial n1 factorial n minus n1 factorial and p to the power n1 q to the power n minus n1. So very good. So actually we have gotten the sum again. So this thing again is the binomial sum, where that was actually equal to p plus q to the power n. So we just replace this here. You see, mathematics is so interesting, and some things that look very difficult become really easy if we do some simple tricks. So we write p plus q to the power n with a partial derivative behind this, and we just compute this partial derivative. So we get p n p to plus q to the power n minus 1, and if this thing is 1, how bigger powers you may take, it always remains 1. So this thing is 1, and 1 to the power n or 1 to the power n minus 1 or whatever, it will remain 1. So we just write now an average that is equal to p n only. This is a very important result. So the average value of number of particles, number of steps, not particles but number of steps to the right, is p times total number of steps. Okay, so you can verify this for any number of steps. Average number of steps to the right equals the probability of any step to the right times total number of steps. This is a very important result, so we can somehow enumerate it. I call this equation B. We will be able to use it again. Okay, and your assignment is small assignment. You should calculate n2 average, the average number of steps to the left, and you should calculate it, and you should get the value equals n times q using the same arguments, same method that I used. And if you now calculate sum of these two, n1 average plus n2 average, you will get n times p plus n times q, and that is, again, we take n common, and p plus q is 1, so that is n. So average number of steps to the right plus average number of steps to the left is the total number of steps. That simple it is. That simple it is. Okay, and you can also calculate average displacement. So that would be m average, and that would be n1 average minus n2 average, and that would be again n times p minus q. So you can enumerate this equation. Okay, I should have enumerated nq as c, n2 average above, and then I can enumerate this thing as d. So we can use it later for other calculations. Now we calculate dispersion. Dispersion of the distribution. And dispersion is given by delta n1 squared and averaged. So we will calculate the deviation from n1 and then we square it and then we average it. So there is this easier method to calculate, so that is delta n1 squared and average, that is basically equal to n1 minus n1 average. This gives us the deviation from the mean value, and we then square it, then we average it. And if we open this square average thing, so we will get n1 squared average minus n1 averaged square. So you should be able to see the difference in between these two terms here clearly. You should be able to clearly see what is happening here. So in first term we have first square and then average, and the second term we have first average and then squared. So this will give us the dispersion. Now what we have, if you see above, we have n average and one average, this quantity already. And we need to calculate this thing, n square average, so that we can calculate at the end of the day the last thing, that is this thing with 3 arrows. Okay, so I put 3 arrows so that we can know that we need to calculate this, but we have this thing already. We just need to take square of this, and we first calculate this one, and then okay, we'll reach this thing here easily. So okay, so we start. So we now calculate n1 squared average. That would be again the same formula for average values, probability multiplied with that value where we want to get average of, for which we want to get average of, and then summation over all states. The same simple formula all the time. We write this n1 from 0 to n factorial, n1 factorial, n minus n1 factorial, p to the power n1, q to the power n minus n1 times n1 squared. So we call this equation our next number e, and we just proceed. So again we have now n1 squared here, so we want to get rid of this, so we use some simple trick for this. So okay, we just write this thing here separately. So we have n1 squared times p to the power n1, and we can decompose it n1 times n1 p to the power n1 and if we decompose it, and this thing we did when we were calculating n1 average, So we wrote it partial p times partial or partial p to the power n1. So we just put this value here. So n1 times p multiplied with partial or partial p and p to the power n1. So this is simply from that step. Whole thing is replaced by this whole thing here. So that should not be confused what I did. Okay, and then what more we can do here? So we have p to the power n1 here and one n1 here. So we just combine these two, because we can take this inside this differential. This is a different derivative, so n1 does not affect if we take it here or outside, so we just move it in. We just move this n1 here. It will not make any difference in calculations. So what we do, p partial over partial p, this one, and we write okay n1 p to the power n1. So again we see that we can somehow write this thing as again p partial over partial p p to the power n1. So we write it in the next step. So we write p partial over partial p, and inside we have again p partial over partial p, and at the end we have p to the power. Okay, so I can write them combined p to the power n1 here. So now this is double derivative kind of thing, or not double derivative but derivative squared. So we write it like that, p partial over partial p squared into p to the power n1. And this is our n1 squared e to the power n1. So we just put this thing that we just evaluated back to our equation E. Here we have n1 times p n1, so we just replace it there. So we have n1 squared and its average, put it in E. I write put in E. So we will get and 0 to E and and factorial divided by n1 factorial n minus n1 factorial. So here it comes p times partial over partial p squared p to the power n1 q to the power n minus n1. So if we move this now before the summation, it will not make any difference. So we move it here, p partial over partial p whole squared n factorial divided by n1 factorial or n minus n1 factorial. So we get the sum back, the original sum. You see, all the time we are doing some mathematical tricks and we get the sum back. So again we can replace this with p plus q to the power n. So this is the advantage of knowing about binomial distribution. So this is exactly binomial distribution sum, and now we just apply these derivative squared onto the system. So we do so I write p partial over partial p, and again p partial over partial p plus q to the power n. So we have to apply this two times. So first time we write, okay, p partial over partial p, and when this applies to this sum, so we get this p remains as it is, and then n times p plus q to the power n minus 1. And now we can apply this thing to this whole thing here, what is inside, product rule or whatever you call it. So p inside, so we have to differentiate by parts. So first time we differentiate with respect to p and leave the other thing as it is. So we applied here partial of partial p of p is 1, and this remains as it is, and p plus q to the power n minus 1. And then with the plus sign we apply, now we leave this p as such and apply pn as such and apply the derivative on this second term, this term now. So when we apply, what we get n minus 1 times p plus q to the power n minus 2. So now we need to simplify everything. So this thing is 1, this thing is 1, so what remains, we write n1 square average is equal to p times n plus, so here only remains n, and here we have this term remaining, plus p times n times n minus 1. That's it, nothing else is remaining. Okay, we can take n common out of everything, so we get 1 plus pn n minus 1, and we get np, so we have 1 minus p plus pn, and this 1 minus p, you know that this is p plus q is 1, so 1 minus p is q, so you can write it q. So here we write np, so q plus pn, and further you can write it as npq plus np squared. And you know that np squared is what? Np, everything squared. If you remember, this is average value of n. We wrote it in our equation b, and one average is p to the power n. So we just put it back here. So our n1 squared equals npq plus n average squared. So now if we move this to the left hand side, we get n1 squared minus n average squared. This is equal to npq, and this is actually, if you go back a little bit and look at this term here, so this is again this is the right hand side of this equation. So this is basically our dispersion. So we can write everything this here, just manipulating the terms, we get the dispersion directly. This is our delta n1 squared average, delta n1 squared average. Dispersion. So our dispersion is, in terms of n, p and q, it is simply the product of these three terms. This is also our very important result. Okay, so now we calculate the standard deviation. Which is basically square root of dispersion. So we name it standard deviation, we call this partial n1 steric, and we write it, okay, delta n1 steric square root is basically delta n1 squared average square root. So this is our square root of npq. So our standard deviation is npq square root. And the relative width of binomial distribution or random walk problem that is delta n1 steric, that is standard deviation, divided by n1 average. So we have both values now in terms of npq. So npq square root divided by np, and that we will get as 1 over square root n square root of q over p. This is also a very important result. So let's summarize what we have learned today. If I put a really small summary of today's outcomes. So we learned what is a random walk problem, in one dimension. So we did all the mathematics with some fancy animation to get an idea. So it is very easy to understand what is random walk in one dimension. Actually it exists in 2 or 3 dimensions, and it is a lot difficult to do these calculations in 2 dimensions or 3 dimensions. But the conceptual basis you should know that anything that starts from some original initial point and then moves randomly to other places, and then it has a probability of coming back to the original point, and it has a certain probability of moving it away. But we uh, somehow computed that the probability of being in the middle or where it started from is the highest, and the probability away from the main position or starting position decreases, and its probability is low away from the initial or starting point. And we calculated some mean values and some dispersion relationship, and we also calculated the average the relative width of the binomial distribution. And what else we got to know about this problem? So we also got to know that binomial distribution, it has been given a name of binomial distribution because it is somehow similar to binomial distribution, but this is not exactly equal to binomial distribution. So random walk problem has no summation in it, but the binomial distribution actually has summation in it. Okay, and I will give you some assignments related to binomial distribution. And now you get to know that what you were using beforehand in the previous assignment was not what I asked you to do. I asked you to do simple probability things, and now we are actually into the binomial distribution, and we will encounter this binomial distribution in statistical physics also later, some other, and we will study the systems with large number of particles in it, and we have to modify it somehow to get some other kinds of distribution. So this will follow. Thank you very much.